Well, welcome to another edition of Physics 264 pre-lab tutorials. I'm Dr. Steve Brule. Today we're going to study operational amplifiers. We'll see why operational amplifiers are so important in electronics. We'll explore ideal and actual characteristics of an op-amp. We'll learn the two golden rules for op-amp analysis. And we'll analyze the inverting amplifier and show how to breadboard the circuit. And finally, we'll analyze the non-inverting amplifier, but we won't breadboard it. Well, what are operational amplifiers used for? What is our... I have to fix that. An operational amplifier is a high gain difference amplifier. What that means is that the output of the amplifier is equal to whatever the gain of the amplifier is times the difference between these two pins on the op amp. So if we had a gain of 2, let's turn that off. If we had a gain of 2 and we had these two voltages on the input, the difference is 3 multiplied by the gain, we get 6 volts on the output. Well, an LM741 op amp has a gain of 100,000. So if we have a difference of 3 volts on the input, we get an output of 300,000 volts. Well, how can that be? It can't be. The op amp can only go up to its supply voltage. But why would we want an amplifier with such high gain so that we'd have a tiny, so if you had 1 volt here and 1.00001, I think, volts, so the difference is is how many millivolts? 100th of a millivolt. Then we're going to get 1 volt on the out. How are you going to amplify 100th of a millivolt? Why would you want an amplifier like that? You'll see. It's got a ton of applications. This is just a book that I took a look at, and it's got 896 pages of op-amp applications, and you can go on the web and you'll find zillions and zillions. They're used all over the place. Well, the first application we'll look at, we're going to run through a few simple applications, is a comparator. If you have a comparator is a device that compares two voltages and either gives a high voltage for if V1 is greater than V2, and if V1 is less than V2, then it'll give a low voltage, and the output of the op amp will be the supply voltage. This is usually not used for an op amp because we have dedicated comparators that work better than an op amp does in this configuration, but I just wanted to show you what an op amp would do if it wasn't hooked up to any resistors or anything. Low gain amplifier, that's what we're going to look into today. I won't go into more of that. Voltage follower, what that does is it changes the input impedance, so if you need a high input impedance, that's the way to go. Audio and video preamp, so here we have two op amps in this audio preamplifier. So this would be the preamplifier. We've got some there's the transistors right there that are the power amplifier going to a speaker, but they're using op amps as the preamp in that amplifier. A summing amplifier takes the voltages on here, and then the output is the sum of all these voltages. That one would be inverting actually, so it would be minus the sum of all those. This is an integrator, so that integrates whatever the voltage is at the input. We're going to look at that next week. This is a differentiator that takes the derivative of whatever is on the input. Analog computers, I spent a year of my life working on analog computers back in the 80s. That was before we had computers that were really good at doing simulations. And this particular analog computer solves that differential equation using op amps. Exponential and logarithmic output. So here we have some input, and the output is the exponent of the input. Here we have the the logarithm of the input when we look at the output. Here's a waveform generator. We can either get a square wave or a sawtooth. Capacitance multiplier, look at that circuit. What it does is it takes whatever capacitance you have and then it multiplies it and makes it seem like you have a really big capacitor when you don't have such a big capacitor. This is a voltage clamp. I won't tell you what that is. An ideal diode, it takes away the forward bias of a diode so that when you put your input you get exactly It goes right down to 0 instead of using that forward bias business. Active filter, so this is a active low pass filter. You can get band pass filters, you can get high pass filters, you can tune them however you want. There's zillions of applications of these things. Well, let's look at the ideal characteristics of an op-amp. First of all, we would have infinite voltage gain. The reason why we want a very high gain on our op-amp is because we want the voltage difference between these two pins to be effectively 0 when the op-amp is functioning. That's in every case except for the case of a comparator. So these two voltages should always be almost the same. And if we have infinite voltage gain, then they will be the same. But if we have 100,000 of gain, then the input of these two pins will be very, very close, still essentially 0 difference. We have infinite input impedance. That means that there's no current that leaks into the op-amp from our inputs. And we always do get a little bit of current, but we essentially say that it's 0 and it's okay. 0 output impedance. That's not really the case in op-amps, but in practice, as long as we're not asking the op-amp to deliver too much current over our load, we can assume that it has infinite or 0 output impedance. Infinite bandwidth. This is another one where no op-amp has infinite bandwidth. That means that if it had infinite bandwidth, that would mean that we could put any frequency on the input and the output would do whatever it's supposed to do without regard to however fast the op-amp works. But in real life, all op-amps have bandwidth limitations, and we'll look at the limitations of the 741 in our lab this week. And 0 input offset voltage. That means that if we have no difference between these inputs, we should have an output of 0 because we have a gain. Even if we have a gain of 100,000, if we have 0 difference, we should still have 0 output. But in practice, there always is a little bit of output voltage, and that's why most op-amps come with an adjustment pin where you can dial that out if you need to. Well, our op-amp, as most op-amps work, use a positive and negative power supply. So this is just this supply to the op-amp, which has nothing to do with the function of the op-amp. It's just letting it run. Okay, the two golden rules of op-amps before we start analyzing are inputs draw no current. We already talked about that. We don't want any current used up by the op-amp from the input. And when operating, the difference between the inputs should be 0, except when it's using as a comparator, which we won't really do anyway. Okay, an inverting amplifier. So here is the inverting amplifier hookup. Let's analyze how this works. So from the golden rule number 2, we know that these two pins are going to have the same voltage, and since one of the pins is going to ground, we know that this pin right here must also be at 0 voltage. It's not directly connected to ground, but the op-amp will make sure that it stays at that voltage. Okay, so then we can calculate the current through this resistor right here just using Ohm's law. It's the voltage drop across this resistor divided by the resistance of the resistor. And the voltage drop is just Vin because we know that this point is 0. So the difference between this point and this point is Vin. Okay, and since there's no current, this is golden rule number 1, since there's no current that goes through that input, then we can say all the current that comes through this resistor has to go through that resistor. That's golden rule number 1. So that means that we call that the feedback resistor. We're getting negative feedback there. The current through the feedback resistor is equal to the current through the input resistance. We can then calculate the output voltage from Ohm's law. We put our positive lead here and negative lead here, and the voltage drop is in this direction. So it's V of this minus the V out. We end up with a negative V out here because of that. This is 0. And that's going to equal the current times the resistance of that voltage just by Ohm's law then we substitute the current right here is the same as this current. So we just substitute that in, and we end up with this equation for the output voltage as a function of the input voltage. So it's just the ratio of those two resistors, the feedback resistor over the input resistor. Well, let's breadboard this circuit and see how it works. So here's the pin-out diagram for a dual inline package 741 chip. And I just rotated it over so that this looks in the same orientation that I have here. Now notice that we've got, here's our V minus pin, and we're using blue. That should be blue there. It looks almost purple. But that's our negative 12 supply voltage, and I'm just running from that pin number 4 to our negative supply rail, and I'm going to keep that as a blue wire so I know not to get that confused with my signal path. Okay, let's see what else. We've got the positive VS. Where is that? No, that's positive V positive. Yeah, here we go. V positive is right here, and that's a red wire. It doesn't look red in this video, at least to me, but it was red in the real life there. So we want to keep that red for our positive 12 supply voltage, and that's on the V plus pin. So now we've got the supply voltage going to our op amp, and we're ready to go. The black we're going to keep as ground. That's over here. That's the ground rail, and see how that is connected to our ground rail. We don't have that connected to anything yet, but we will, and all of the external equipment will be forming a little tree at that external jack. Okay, so now I'm going to connect pin 3 as according to this diagram. The positive pin should go to ground. So there's the positive pin, which is pin 3, 1, 2, 3. So I've connected that to my ground rail there with a black wire. I'm using black wire so I don't get confused with my signal path. Very important. Okay, here's the feedback resistor is going from the output. There's the output pin, which was 4, 5, 6. And the input, the negative input, which is pin 2, so there it is going from pin 2 to the output pin, which is 6, and I just put in a 10K resistor for that, just for this demonstration. Now I'm putting in this resistor going from, it's connected right here to the feedback resistor, and then along that row there, and then it's just going to come out to here where I'm going to connect to an external jack. So that's RN, and I'm just using 10K again. All right, so here I've connected the that input right here to an external jack where I will put in a DC voltage so I can test the output, which is coming out here. See, I'm using a yellow wire now. That's just for the things that aren't powering the jack, the 741, or that they're not the ground. So we're using some other color. It doesn't have to be yellow, just it can't be blue, red, or black. Okay, what else do we have? The green wire now is at this pin, on the output pin. So there's the green wire. So then we'll have that for the output of our op amp that we can take a look at. So the let's see, what am I doing? Power supply, there's the power supply it's coming in here. You know how that works. And that's creating the power on our rails, which powers our op amp. This is the DC power, I'm calling that VN, and we're using this DC power supply to go in right here, and that'll be the input of our op amp. Here we're using an external jack to come out of the op amp, and then we're going to take that to our meter so we can look at the voltage that's coming out of the op amp, and this is the common ground as we've discussed. Okay, let's test a few voltages for this particular op amp. This would be an inverting op amp of gain -1. Okay, So let's see if we really get a gain of -1. Here we have the input voltage of 0 volts according to my DC power supply, and I'm getting 0.4 millivolts, which is pretty close to 0. I'll go with it. So now I've got 1.6 volts on the input, and I've got -1.591 volts on the output of my op amp. That's good. It's a gain of -1. Here I have the input of 4.2. The output of the op amp is -4.25. Pretty good. Input 6.3, output -6.3. Again, we had the gain of 1. We're getting close to our supply now, and you're going to see something happen. Here we've got input of 10.3, output of -10.3. But look at this. I put input of 17, and I still have my output of 10.4. So what has happened is the op amp has become saturated. It cannot put out a voltage that's greater than its power supply voltage. That's one of the characteristics of op amps. If you want an op amp that puts out a higher voltage, you'll need to have a higher rail voltage, or supply voltage. Okay, well, let's change Rn to 5K. I did that by just putting two 10Ks in parallel, so that's 5 kilo ohm resistance on the input, which gives us a gain of -2. Let's see if we get a gain of -2. Here's the input of 3, output of -6. Input of 4, output of -8. Looks good. Input of 7, output of -10. What happened? What happened is the op amp can't put out a voltage greater than its supply voltages. So it saturated once I had an input of 5.2, and anything above that 5.2, I'm just going to get the rail voltage. Let's change the feedback resistor to 5K and see how that works. So now our gain should be -1/2. Is that the case? I put in a 7.3 on the input, and I get -3.67. That's pretty good. Put in 10.5 volts on the input, and half of that is about 5.24, and that's good. And we've got the negative sign because we've got a gain that is negative. Now we're above our supply voltage, but we're still hanging in there with the op amp working, and that's because it's okay to have a high input voltage because the op amp doesn't even see that voltage. It just sees the current that's coming in. It's making sure that that voltage is 0 as that current passes by its input. So it doesn't even know that you have 13.3 volts over on the other side of that input resistance. So it's all right. It just can't go higher than that on its output. So here we have an input of 18.5. Again, we have a gain of -0.5. So we take half of that, and that's about right. We got the negative sign. And finally, we're asking the op amp to give us 12.25 volts, but it can't because it's saturated. So there it is, saturated at its supply voltage. To get a negative input voltage, which you'll have to do in the lab, you just reverse the polarity of the input voltage. So now this becomes the ground connection going to that ground tree. The ground tree is now going to the positive. Let me say that again. The ground tree that we have on our breadboard is coming right here, and we're saying that now that is V equals 0, which is the positive. So our negative terminal of the power supply is now going below that. So then when I read 2.5 on my power supply, it's really giving out a -2.5 to my breadboard in reference to its ground. So I'm putting in -2.5, and if I have a gain of -1/2, then I get a positive voltage out of the op amp, which is right, and it's about half of that. So now I just have done 2 of them now. I put in a voltage of -19.4. Again, it's negative because these 2 terminals are reversed, and then I take half of that, and I get that, and it's positive because it's inverting the negative sign that I have on the input. Okay, and another thing you're going to have to do in lab is put an AC voltage on the input here, and we're going to do that using a waveform generator. Okay, so that's coming in here and going to the input of my op amp. And now to look at the output, instead of using a DC voltmeter, I'm going to use the oscilloscope so I can see the waveform. So I'm looking at the output right now, but it's not telling me much. It tells me that I've got a sinusoidal output, but I can't see the phase relative to the input. So in order to see the phase, I have to look at the input and the output simultaneously using the dual trace mode of our oscilloscope. So I've set that to dual trace so I can see both of the signals on the screen at the same time, and you'll have to do that in lab. Okay, you probably will have to push in that negative 20 dB button on your function generator because the output is too hot and it's going to saturate your op amp if you don't do that. What else do we have? Oh, why don't you, while you've got this all set up, test the bandwidth of your 741 op amp. And you can do that by just turning up the frequency of your function generator and keep putting in a higher and higher, I can't remember which one is which, but you put in a higher frequency to the input of your op amp, and then you look and see if the op amp is keeping up. And it'll keep up probably up to about 10,000 hertz, and maybe above that you're going to start seeing it somewhere above that. You'll see the output starting to sag because the poor little 741 can't operate that quickly. Let's analyze the non-inverting amplifier. Well, this is the schematic for a non-inverting amplifier, and from golden rule number 2, these two terminals will always have the same voltage. And since I have Vin on our positive input terminal, that means that Vin is also there at the negative terminal, because the op amp, when it's functioning, it will maintain a zero potential difference between those 2 points. It's really very, very tiny, but it's essentially zero. Okay, so there it is. V of this negative input to our op amp is the same as Vin. So that's what that says. And now, since Vin, that's positive, I put in a positive Vin, so now my current is going this way through R1, and I use Ohm's law again to find out what that current is. And then since we have golden rule number 1 that says there's no current that's going to go into that terminal of the op amp, then we know that the current through this resistor has to be the same as the current through that resistor because they're in series, as long as there's no current that leaks out. Okay, so now we can find the output voltage is just the sum of these two voltages. Here's 0, so it's going to be this voltage plus this voltage. So I2 R2 plus I1 R2, but I2 is equal to I1, which is equal to this. So I get this equation, and finally my output voltage should be equal to that. And we're going to let you breadboard that circuit on your own. Hope you've enjoyed this show.